Welcome to the LeetCode Larry Show. I am your host, LeetCode Larry, the only person on the planet named LeetCode Larry whose name is not actually Larry. And today we're going to be doing a very fundamental tree data structure problem. It's called binary tree Inorder Traversal, and it's number 94 on LeetCode's problem list. So there are a couple of ways we could tackle this question. Two main ways are to use recursion, and another way is to use breadth-first search using a stack. Well, could we use a queue? No, we would use a queue. We would use a queue as opposed to a stack. In depth-first search, we'd use a stack, and breadth-first search, you can use a queue. Now, you could also do a non-recursive iterative depth-first search using a stack, but today we're just going to do a simple no stack, no queue. We're just going to do some recursion. Now, it's worth mentioning that there will be a call stack internally being called. So you could say we're using a stack for memory, but we're not going to explicitly define a stack. So how do we do such a problem as an Inorder traversal? What does that even mean? Like, what is the Inorder traversal? Well, they have a pretty bad example in my opinion here. They just have 3 nodes. But the definition is basically this. When you process a node, first you process the left subtree, then you process the node itself, the root, then you process the right subtree. That's what the definition of Inorder traversal means. Now, we'll get to pre-order and post-order in other videos, so I don't want to be too confusing. So just one more time, I'll say that explicitly one more time. When we're processing a tree of nodes, first, when we look at a node, when we look at a root node, first we're going to process this left tree, the root itself, and then the right tree. So let's take a better example here. So I drew a pretty poorly drawn tree here. It's very hard to draw with a mouse, by the way. Don't recommend it, but I'll find a better way in the future. But here, let me explain how Inorder traversal works. So in this case, we would first process this. This is the root node, the 5. Obviously, this is the root node. When we're processing this root node here, in order to do an Inorder traversal, we want to process the left subtree first. That's this tree here. Then the root itself, then the right subtree. That's this tree. Now in this problem, what do we mean by process? Now processing can mean a variety of things, but for now it just means add it to an array. So you can see the output here is literally just an array of the values of the nodes we are going to process. So if we walk through this example here, let's go ahead and just walk through this example and see how an Inorder traversal works on this tree. So first, we process the top node, the root node. Well, I guess we shouldn't say process. We look at this top node. And then, since it's an Inorder traversal, we're going to look at the left subtree first. We're going to process the left subtree. And so when we look at this left subtree, we actually go down to 3. We recurse down the tree. We're using some recursion, as I said. As you can see, this tree has all trees, as a matter of fact, have a recursive structure. So this left subtree is actually a tree itself, just like the entire tree here. So we go down to 3. And what do we do with 3? Well, we notice that there's still a left tree. In this case, there's no right tree, but we'll get to that in a second. So then we keep going down and keep recursing down the tree. So we get to 4. What does 4 have? Well, 4 has 2 trees, 2 subtrees, 2, well, you can call them child nodes here, but they're 2 subtrees of 4 itself. So one more time, we're going to go down. We're going to look at 10. Now 10, since 10 has no children, you can go down to the left. I mean, you can just say that it's null. So you go back up to 10. Since 10 has no children, we're going to just add it to this list. And then when we're going to go back, since we're done with 10, we're going to go back up to the roots of this tree here. So like I said, if we think of this as a tree itself, we process 10, we add it to the list, then we go back up to the root here. We're going to add this root value, 4, and then we add the right value, the right child's value, which is a 1. Now, again, if we do some backtracking here, I'm using that term a little loosely, but if we go back up the tree, we see that we are still working on a tree here, because this left subtree of the whole tree is itself a tree. So, since we already processed the left tree of this tree here, now we can process the root, the 3. Okay, but now we want to go to the right. But if we look at the right, we see that it's null. So we can go ahead and then we're done with this processing this whole tree. So now we're back up to the root. We've already processed the whole left subtree. Now we're going to, add the value of 5 to the list itself. So now we're going to process the right subtree of this whole tree here. So what is the root of this right subtree? It's 7. And does 7 have a left child? Yes, it does. So once again, it's according to, and for the Inorder traversal, we're going to process its left subtree, then the root itself, and then the right subtree. So here, the left subtree is just this node 9. If we look at this node 9, it has no children. So we can go ahead and add it to the list. Now once again, in code, we can actually check the left subtree to see if it's null. Then we can go back up to the root. And then once we process the root, once we add the root value to the list, we can go ahead and check the right subtree. Again, it's going to be null. So now we can go back up to the 7. So we've already processed the left child, the left subtree of this tree with the root 7. So now we can add 7. Now one more time, we're going to go ahead and go down to the right. Excuse me, I'm going to look at the right, and we're going to see that the right is null. And so we're not going to add anything. So we're going to go back up to 7. And now, since we're done with 7, we're also done with 5. We've processed the left subtree first. And then we got this. Then we processed the root, which is the 5, and then we did its right subtree. So that's the logical, that's the sketch and the logic behind Inorder traversal, excuse me. So how are we going to do this in code? We're going to do this in Python, but what's the logic here? Well, you want to go ahead and make a helper function. This way it'll be much easier to do recursively. I think it's the only way you can do it recursively. We'll go ahead and do a helper function called Inorder. What's Inorder going to take? It's going to take a root, and it's going to take a result list. So we're actually going to initialize a list called result. And this is what we want to return. And Inorder is going to act on this result. Actually, we're going to do self.inorder because that's how Python works. Self.inorder root result. So what is it going to do here? It's going to do the logic we just went over. It's going to process the left child, the left subtree extending out from the parent. Then it's going to process the root itself. It's going to add the value of the root to the list. And then it's going to go ahead and recurse down the tree to the right child. And this result, you can append to it. And in Python, the way it works with the list, if you pass in this result to this method, the results will be modified. It'll be mutated. And anything we add to it, once we're done working on the result, we will be able to return. Okay, I'm kind of messing up. Stop saying this. So basically, what I'm saying is, if you do some logic in this method, you mutate this array, and you do one, and you end up adding 1, 2, 3. Once you come out of the array, the result, the list will still be will have the values that you've added to the array, or a list. In Python, it's called a list. It's kind of confusing, a lot of confusing nomenclature. But that's key here. That's why, partially why we had to create this result here and create this extra method. So what do we do here? There's only 3 lines. Kind of simple, but not simple if you have never looked at it before. So we want to define Inorder. So we want to recursively call this Inorder function. How do we do that? How do you do recursion? So like I said, there's a recursive structure here. We're looking at this tree. What do we do here when we look at this root node? Just think about it for a second. We want to perform the Inorder traversal on the left subtree, the left child subtree. And then we want to add this value to the list. And then again, we want to perform the Inorder traversal, but this time on the right subtree. So how do we do that? So let's do that. Self.Inorder. Well, first we want to check if root exists. Self.Inorder root.left result. Oh, I should also add a self here. Because in Python, for any methods, you're going to have to add this self parameter as the first parameter. Any non-class methods, I guess we can get to that in a later video. But okay, self.Inorder. So like I said, at first we want to do a self.Inorder on the left child of the tree. That's what we want to do first. But what do we have to do before we do that? Because I added this extra line of code here in line 18. What is ifroot doing? Well, let's say we get down here to 10. Before we can actually add 10 to the list, what do we need to do? We need to check the left child. So we're actually going to, in our logic, we're actually going, let's say our root is this 10 node here. We're going to do an Inorder on the left. It doesn't matter that left is null. We're still going to recurse down here and do an Inorder. But what do we want to do here? Well, if it is null, then obviously we're still going to go into this method. But we're going to skip the logic. So we're not going to do this whole processing that we do here, the self.Inorder. Instead, we're just going to move on and recurse back to this 10. So what do you do after you do a left child? Like, let's say we just process this null value. We want to come back up to this 10. What do we do here? Well, once we're done processing the left child, we can go ahead and just do a result.append root.val. Now root.val is going to hold the actual value of the node. In this case, the way LeetCode does it here, the tree object, the tree node, is going to actually contain an integer as a value. I mean, Python's typing is a little bit annoying, so you can't really see that explicitly, but they define value here as 0, so you're just going to add this, it's not really an integer, I guess you would just call it a number in Python. You're going to add this root.val number to the list. So this is the only line where you're actually adding a value. And then what happens when you actually add the value here? Well, when you add the value here, so that we're at 10, then we want to recurse down to the right tree. So self.Inorder root.right result. Just like I said before, the code will enter this method. It will take this null root. Root will be a null. And it will execute this method. But we're going to check if root is null. So, I mean, there's two ways you can do this. You can do if root, or you can do if Root is not none. In Python, actually null you would call none. So that's two different ways to do the same thing. I think actually a lot of people prefer to do is not none. I may change that in the future, but for now we'll just do if root. So if root, so basically just checks if, like once again, if root is not null. That's why I think people like is not none better. It's more explicit. But if that's true, then we're going to go ahead and do the in order on the left, then append the value, and then the in order on the right. So once that's done, we'll go back to for, and we're going to keep doing this recursive structure. So if we look at node 4, we see we've already done the in order here on this left subtree. Then we add 4. Then we go ahead and do a self-done in order on the right subtree. We look at 1. And once we look at 1, we do an in order on the left subtree. Oh, but the left subtree is a null. So we get out of this method and we go here and we append to the list the 1. So we have 10, 4, 1. So that's going to keep happening. And then once again, 1 is going to, we're going to do an in order on the right subtree of this 1. Then we'll be done with this whole left subtree of this 3 node. I say left subtree, left child, kind of using them interchangeably. And then the process continues on until you're done with this whole tree. So that's the whole logic. Let's go ahead and give it a run. All 3 test cases are passing. Let's go and give it a submit. All right, accepted. So once again, that is the in-order traversal of a binary tree. There's another way to do it using a stack to do a depth. This is a depth first search. Is it depth? Yeah, it's a depth first search because we want to go down to the depth of the tree. It's a depth first search solution. There's also a breadth first search where you just kind of do it by level. So you do 5, and you process 3 and 7, and you process 4 and 9, and process 10 and 1. But this way is the depth first search. And so let's talk about the memory complexity and the time complexity. The memory complexity is going to be at most n, so it's going to be big O of n. But why? Well, because at most you're going to actually put 10 nodes on the call stack. If you have just one tree like this, of n nodes, you're going to put all those n nodes on the stack. That'll be the whole memory. That'll be the n nodes will be used as memory. That's the worst case. Sort of I guess you could say the average case. If you have a balanced tree, it's going to be order of log n. Yeah, log n, correct. Yeah, so basically we'll log base 2 of n, I should say, since this is a binary tree. Because the height here will only, well, yeah, so yeah, that's what it's going to be, log base n. So let's say you're doing, well, hold on. Let's edit this out because I'm going to have to think for a second here. It wouldn't be log base n. No, it'll be n over 2. So let's say I have a balanced tree like this. The memory complexity no, I was right the first time. It's going to be log n for memory complexity. You're only going to, when it's a balanced tree. As I said before, the big O of n in the worst case would be n nodes. But in this balanced tree scenario, it's going to be log base n. Log 2 of n, because you're only going to go down the tree to here, and you're going to put those 3 nodes on the stack. Yeah, so it's a good thing I thought of that, because I kind of thought it would be n over 2, but that shouldn't be the case. The The time complexity, same deal. Well, you're gonna have to, actually, the time complexity is going to be O of n, because you're gonna have to process every node in the tree. So that one doesn't take as much complexity as the memory complexity, as explaining the memory complexity, for lack of a better word. But yeah, so the time complexity is going to be big O of n, because you can't get away from processing every node in the tree. Okay, well, but that's it for me, folks, and that's the solution to binary tree inorder traversal. Question 94 in LeetCode. Once again, this is the LeetCode Larry Show. I'm LeetCode Larry, the only person on the planet named LeetCode Larry, whose name is not actually Larry. Cheers.